Welcome to week 11 of the ma135 ma160 calculus. My name is Götz Pfeiffer and this video is about mathematical models. A mathematical model is a mathematical description of a real-world phenomenon. And the language that is used is the language of functions, calculus here, where the phenomenon is described in terms of a function or an equation. Then the model can be used to understand the real-world phenomenon and perhaps to make predictions about future behavior. Diagrammatically, one can maybe distinguish here a real-world layer from a maths layer, where in the real world you have some kind of problem and then you translate it into the language of mathematics, into calculus language, for example, using functions to formulate a model, which you then, using mathematical tools, can use to solve, come to a conclusion, which then maybe you can interpret as some prediction in the real world, which then can be tested in real world terms. There's a principle and work here which is known under many names, for example as Occam's razor, which calls for simplicity in the sense that a good model simplifies the reality in order to permit the mathematical calculations, and at the same time, of course, it needs to be sufficiently accurate to provide conclusions that are of any value. But in that sense, mathematical models are approximations to the reality and they have their limitations, and it's important, whatever model you use, to be aware of the limitations of the chosen model. I want to look into this in a bit more detail here in the context of differential equations. In calculus we use functions to model real-world aspects, and sometimes these functions arise as solutions of differential equations. This is an extremely powerful tool because believe it or not, the laws of nature that govern our universe, they are of a kind that can be expressed in terms of differential equations. So differential equations and calculus has allowed us to learn a good deal about the world we live in. And part of that is the fact that the differential equations used as a language make it extremely easy to describe quantities in terms of their rates of change. Our standard favorite example is that of a population that grows at a rate proportional to its current size. As a differential equation, that's one of the shortest formulas you can ever imagine. It sets the derivative of p equal to some constant k times p. We know from there that we can solve this to get an exponential function as a solution for p, but the point here is the compactness of the language, how it allows us to describe processes and the rates of change in a very small space. And that's the selling point here, because most differential equations cannot be solved explicitly. We've seen a few, but these are like simple differential equations. You cannot always expect a solution for a differential equation. However, it is possible to argue with the differential equation, to use the equation itself as a model and derive properties of the solutions without having an explicit solution at hand. And even beyond that, even if an explicit or precise formula isn't available as a solution, then one can use numerical approximations to solutions of a differential equation to learn more about the process it describes. And I want to look at a few examples here, starting with predator-prey systems as an example of a system where two quantities, or here two populations, interact. Some eat, some get eaten. They interact with each other, and this interaction can be described by a pair of linked differential equations. So, for example, let's consider a population of wolves, W, and rabbits, capital R, that share a forest habitat. And the rabbits have ample food supply and would, in the absence of wolves, in the absence of predators, grow at an exponential rate, at a rate that is proportional to their current size. The wolves, on the other hand, prey on the rabbits, and in their absence they would die out at a rate, they would decline at a rate proportional to their current size. So that gives a differential equation that describes the rate of change of the wolf population as minus a positive constant r times the current size of the population. Now, with both species present in the forest, the rabbits get eaten by the wolves, and the wolf population grows as an effect of this, and the rabbit population doesn't grow as fast anymore. And the rate at which rabbits get eaten by wolves is determined by the number of opportunities and by the possible encounters between rabbits and wolves, and that rate naturally is proportional to both the size of the rabbit population and the size of the wolf population. So it's proportional to the product of the two, in the sense that the more rabbits there are, the more opportunities for wolves to meet rabbits arise, and the more wolves there are, the more opportunities arise. And total, the number of encounters is proportional to the product of R and W. And this leads to differential equations which describe the interaction between the two species and the rates of growth of those two populations, taking the two effects into account, starting with the exponential growth there, and then this growth being influenced by the predator-prey behavior at a rate proportional to the product of the current population sizes. So we have the rate of change of the rabbit population is k times r minus a constant a times rw, and the rate of change of the wolf population is minus r times w from before, plus a constant b times r times w. And here a, b, k, and r are positive constants. So again, that's a complex system, and now we're looking at two quantities, two population sizes which influence each other, and they're compactly described by by a pair of short differential equations, which I don't think they can be solved, but they can be used as a model, and they can be used to argue about this system. Let's be a bit more concrete and provide specific values for these constants. Let's say k is 0.08, a is 0.001, R 0.02 and B 0.00002. That is, the two differential equations now have this concrete form with precise numerical values for the constants. And one thing one can do, for example, is look for equilibrium solutions. Look for stable stable values of R and W, which won't change over time. Stable, not change, no change is no change is the derivative is zero. Here we have a formula for the derivative of the rabbit population and the wolf population, and if so these derivatives are zero when those right hand sides are zero, and in this right hand side in the formula for the rabbit population you can take R out as a common factor. Here you can take W out as a common factor. You get a system of equations which you solve for W equal to 80 and R equal to 1000, resulting in these two derivatives to be zero. So from there, the population won't change. This is an equilibrium solution found by just looking at these equations. One can do more analysis and find other properties of solutions, and maybe through a numerical simulation one can find that when you start with 1,000 rabbits and 40 wolves, the populations evolve in cycles. The rabbit population grows. The more rabbits there are, the more rabbits get eaten, and the more rabbits get eaten, the faster the wolf population grows, and that brings the rabbit population down. And these are cycles that repeat themselves over and over again as one possible solution of these two differential equations. Enough of that. The other example I'd like to look into under the current circumstances is a simple model that can be used to model a pandemic or a virus outbreak. This is the so-called SIR model, where the population that is affected by the outbreak is partitioned into three classes. There's susceptible, there's infected people, and there's recovered people. And one aspect of the simplicity of the model is that there are only two possible transitions. There's a susceptible people become infected at a rate that is governed by a constant B, and infected people recover after a while or at a rate that is described by a constant A. There's also part of the model is the assumption that the population size doesn't change over time. The sum of Si and R remains constant. And then B is the rate that describes the contacts and the rate at which infections take place. And A is the recovery rate or the cure rate, which is inversely proportional to the period of infection. And similar to the model we looked at before, the predator-prey situation, where we had two differential equations describing how the two populations interact with each other, here we have three differential equations describing how these three parts and these three classes inside the population interact with each other, in the sense that people transition from the S class into the I class, and then they transition from the I class into the R class. And this is described by three differential equations which express the rate of change of each of these three parts in terms of the current sizes of other parts. And maybe we start with the last equation here, which describes the rate of change in the recovered class as being proportional to the size of the infected class. That's a simple equation which I guess makes sense. The recovery based on the length of the infectious period, the more people are infected, the more can recover. Or the less people are infected, the less need to recover. The rate of change in the R class is proportional with this constant A to the size of the infected class. That's the third equation here. The first one describes how susceptible people become infected. So this describes the rate of change in the S class. And the S class naturally becomes smaller over time as more and more people catch the disease. Less and less remain susceptible. And again, this the rate of change here is described as being proportional to the opportunities, to the possible encounters between infected and not infected people, which is proportional to the product of the sizes of these two classes, S and I. So the rate of change in the S class is governed by this B constant, and it's negative, and so it's B proportional to S times I, and the way the formulas are set up here, this is normalized by capital N, the total size of the population. And then from there, under this assumption that the total size S plus I plus R remains constant, remains the same number N throughout the entire period of time, the rate of change in the middle, in the I class, must balance out the other rates of change. The rate of change in the I class must be exactly the negative of the sum of the rest, so that the overall rate of change is zero. That's where these two terms come from. That's where the two terms come together as the negatives of the other two equations. So that's a simple model, simple, short differential equations describing the transition of people from through different phases of this infection. And again, it's a simple set of differential equations, but there is no exact solution available. So we're again in a situation where we can't work with an explicit function, but we can work with the differential equation and see, can we derive properties of it. And one natural question to ask is, how can we get the number of infected down? When is I decreasing? From the calculus, we know that a quantity is decreasing if and only if its rate of change is negative. And here we have a formula for the rate of change of the I quantity, namely B over n times Si minus A times I. And this quantity is negative if B over n times Si is smaller than A times I. And there, if I is not 0, we can divide by I, and we're left with the condition where B over I must be smaller than capital N over capital S. Where, at least at the beginning of the pandemic, capital S is almost as big as N, so this is basically 1, and B over A, that's in this model, that's what's known as the R0 coefficient, or the R number, which is frequently mentioned in the news as a parameter that needs to be less than 1. That's a conclusion which here can be drawn from this simple model by just looking at the differential equations and using basic calculus properties of the quantities involved. And from there, from this condition, one can derive 3 ways to decrease this R0 number, B over A being smaller than N over S. One way to make this number smaller is to decrease the B number. That's the B is the contact rate. So this decreasing B means decreasing opportunities, decreasing the number of possible encounters between the S class and the I class. That's your social distancing. Increasing the A rate is, in this model, the same as shortening the infectious period, which would call for some kind of cure, and or one way to improve the situation here is to decrease the S number, to have less people susceptible, and that's something that can be achieved by way of vaccination. And other properties can be studied. I want to look at the possibility of analyzing these equations numerically. For example, to study the question, what is S of t in the limit? S being the number of susceptible people. How many? This is like asking the question, how large a part of the population will not be affected at all by this pandemic. And what is S of t in the limit? And since there is no explicit solution for this model, we pass on to a numerical solution. And one way to do this is to replace the derivatives by a difference quotient. Remember, when derivatives were defined, they were defined as the limit of such a quotient, the difference between two function values over the difference between the corresponding x values, and then in the limit we made this difference between the x values, or here the delta t, the difference in time, we made that as small as possible. Here, towards a numerical solution of the differential equation, we reverse this step in a sense, and we go back from the limit, which is the derivative, to the difference quotient, and say, let's take delta t to be one day, then the differential equations become difference equations, and they express the day-to-day change in these quantities, as it is reported on the news. How many new cases are there every day compared to the day before? So we get the formula for s at point t plus 1 in time minus s at point t, being described by this by the formula in terms of yesterday's values. It plus 1 minus it is a differential equation expressed in terms of yesterday's values, or RT, the number of recovered people today, minus the total number recovered yesterday. So this is the newly recovered people is A times yesterday's value of the number of infected people. That's the, okay, this is formulated in terms of susceptible, but then the negative of this daily change in numbers is the daily number of new cases. And on the basis of these formulas, we can simulate this process numerically. For that, we start with concrete values. Let's say we have a total population of 1,000. Maybe that's 1,000 thousands. Well, capital N is 1,000. We start with with a size of the infected people of 3. That's 0.3%, and that leaves 997 susceptible. And at that point in time, at 0.0 in time, no one is recovered yet, so R is 0. And then when the parameters are determined, say A is 0.04 and B is 0.09, then we can use these parameters to compute the values at point t equal to 1 from the values at t equal to 0. So S1 becomes S0 minus B over N times S0 I0. That's the 997 minus B over N times 997 times 3, and that turns out to be 996.73. So there's at that point there's not even a change in terms of so we need to keep digits after the comma here, but you get the idea. We can compute the new values S1, I1, R1 from the old values S0, I0 and R0, and then we do this over and over again. No, we don't. We use a machine, we use a computer for this, and just for the purpose of illustration, here's a computer program formulated in the Python language, which I don't know how much experience you have yourself with computer programming or this particular language, so I wouldn't expect you to be able to read this and understand every little detail of it, but for illustration purposes, this is as short as it is. You set the parameters up here, then you define the model. That's just the 3 formulas which compute the new values, SS, II, and RR from old values, SI and R, according to the formulas as we just saw them. And then this model can be used to iterate this process, say 300 times, compute new values and print them out into a file. Comma separated values, CSV. That's a common format which is understood between different applications. So this program produces an output like this, a list of numbers, how over 300 days these the sizes of these different classes in the population develop, and in particular the drawing program that I use here to draw graphs of functions understands this CSV format, the comma separated values, so I can use this list as it's produced and feed it into the drawing program, and it shows me the development of these curves over time. So starting at 1000, in blue here we see the S curve, the susceptible class. We see in orange the recovered class, which grows to a certain part, and then in red here we see the infected class, which grows somewhat exponentially, I'd say, at the beginning, then reaches a peak and then slowly dies out over the 300 days. And one conclusion one can draw maybe is that in terms of the question being asked, what's the size of the susceptible, how many people remain unaffected at the end of the day? This seems to stabilize near 145 in this model, 145 out of 1000. So, in real-world pandemics are more complex systems. So with a simple model like this, you probably don't get very far. You experience the limitations of the chosen model quickly, but it's a start. It's something that one can work with, and that's what I meant to show the power of differential equations, even when they cannot be solved. Okay. So I hope that this could be seen. Differential equations are a powerful way of describing natural phenomena through simple equations. For example, the predator-prey system that we've seen models two populations by a pair of linked differential equations. The SIR model that we just saw describes a pandemic in terms of 3 linked differential equations. And while some simple differential equations can be solved explicitly, we can work with the differential equations themselves to derive properties of solutions without having an explicit formula for the function that solves it. And beyond that, one can approximate solutions of a differential equation numerically to study the model and compare the conclusions that one can draw from the model with what really happens in the real world context.